Explain plan, CPU steps, concrete, SQL, select count asterisk from sales where product underscore sk equal 31 and store underscore sk equal 3. Explain simplified, aggregate, count. Next line filter product underscore sk equal 31 and store underscore sk equal to 3. Next line column scan product underscore sk comma store underscore sk. CPU mapping step 1 column scan load compress column product underscore sk. Next line load compress column store underscore sk. Sequential reads to cache line friendly. So in CPU, we load the compress column in product underscore sk and load compress column in store underscore sk. And those CPU has those vector unit, execution unit that could execute this. It's sequential reads and cache line friendly. So it's fast and the CPU are able to execute this easily. So first here in SQL, since it's a declarative interface, it's an aggregate count, which means it filter first the product underscore sk equal 31 and store underscore sk equal to 3. Then we do the column scan. Step 2, predicate push down to bitmaps. Bitmap underscore a equal product underscore sk equal 31. Next line bitmap underscore b equals store underscore sk equal 3. Next line bitmap underscore c equal bitmap underscore a and bitmap underscore b. This uses SIMD, bitwise and registers. So the SIMD is the vector, and then it uses the bitwise and the logical operation or execution units of the CPU and the register within it. So that's how the predicate push down to bitmaps. And then step 3, aggregate count equal pop count argument bitmap underscore c. No rows, no tuples, no pointers, just within CPU registers and its internal memory. This is why column stores are fast. So if some CPU were designed to already have those load and store registers and to have memory beside it to execute it immediately without contacting the outside memory. That's why this is fast. So it's specially applicable for modern CPU. BigQuery versus Vertica materialized views. Aspect storage Vertica on-prem/VMs, BigQuery cloud object storage, Aspect execution, Vertica long-lived engine, BigQuery serverless, Aspect MV updates, Vertica incremental, BigQuery incremental, Aspect indexes, Vertica sort orders plus projections, BigQuery no indexes. Aspect bitmaps, Vertica explicit, in BigQuery implicit. Aspect CPU model, Vertica vectorized, BigQuery vectorized plus distributed. So Vertica, it's not distributed, it's only vectorized as its CPU architecture. And the bitmaps are created using explicit model. Indexes is sort orders plus projections, while BigQuery doesn't have that sort orders because it doesn't have like a cache view of materialized view. So the BigQuery or the storage engine or the column oriented storage engine we discussed before. However, the MV updates for both are the same incremental execution long-lived engine for Vertica, because again those materialized view are already on the disk, or in BigQuery it's serverless. So we update by state just like with Redux, and we batch the write to it, right? Because we can't update the the snapshot in storage on premise and virtual machines for Vertica. So they have their own premise machines that they handle. So this company, well, BigQuery, it's a cloud object storage, kind of like S3 with um, PostgreSQL with Supabase. BigQuery twist: BigQuery doesn't expose bitmaps. It uses column statistics plus pruning, relies on massive parallelism. So the parallelism where the CPU architecture execute multiple instructions in parallel. So that's what it take advantage. Conceptually same, operationally different. Why Firestore cannot do this? Core reason: Firestore is document oriented, row based, point read optimized, strongly consistent OLTP system. So it's strongly consistent, kind of like the same with Supabase PostgreSQL, which eventually consistent. Firestore query model: index to document references to fetch documents. Why bitmaps don't fit? No global row order, no column files, no SIMD scan, no batch aggregation. Firestore equal lookup engine, BigQuery equals scan engine. So there's no global row order that will track the state. Kind of like with PostgreSQL, it has like a global and local state. Firestore could have those as well, like global documents and local documents. It has no column files, no SIMD scan. Sorry, this is Firestore. It has no global row order, while Bitmap has a global position order. No column files for Firestore, no SIMD scan or vectorized scan that take advantage of parallelism, and no batch aggregation. BigQuery has that. They serve opposite workloads. Incremental materialized views, the key idea. Instead of recompute enter MV, do apply delta. Example, MV colon sales underscore by underscore product, argument product underscore SK comma revenue. New row arrives. Product underscore SK equal 31. Next time price equal 10. Incremental update. Revenue. Argument 31 plus equal 10. How engines do this? First, buffer new rows, LSM. Second, maintain delta tables. Third, periodically merge. Fourth, rebuild compress engines. This is why MVs are okay in analytics, terrible in OLTP. So it also use or buffer new rows for in LSM, like it maintains delta tables instead of recomputing the entire MV, and periodically merge and rebuild compressed segments. One mental anchor: keep this: OLTP find rows, analytics count patterns. Everything you're learning is a consequence of that. So analytics find pattern because it find the rows based on the position of it on its column, how far it is in column, and all while OLTP find rows. So the exact row that you were trying to get. That's why you need to be more explicit in OLTP. So where you're finally close to click, understand LSM trees, column storage, bitmap, CPU execution, SQL planning. The only missing piece was planning is not equal execution. You've crossed that boundary. Inside the machine, exact chapters you want. To understand aggregate planning, bitmaps, column scans, SIMD, cache lines, and why this all maps to Vertica or BigQuery, the highest ROI chapters are: primary chapters must read chapter 3, instruction level parallelism. This is the most important chapter for everything we discuss. You'll find here why CPUs love simple loops, why branchless code bitwise and OR is fast, how SIMD works conceptually, why bitmap operations are ridiculously efficient, why counting bits beats pointer chasing. This directly explain bitmap n slash or, aggregate planning, why column stores scan instead of seek. Chapter 4 Memory Hierarchy. This explains why column store exists at all. You'll learn cache lines, spatial locality, why sequential scan wins, what cache line jumps actually mean, why random access firestore B3 pointers is low. This maps to column pruning, column compression, LSM sequential writes, why do no pointers to data elsewhere matters. Secondary but useful chapters, Chapter 5, the Pentium Pro and beyond, focus on superscalar execution, out of order execution, why CPUs can execute multiple bitwise ops per cycle. This explains why database lean into CPU instead of disk, why analytics engines are CPU bound, not IO bound. Chapter 6 Multi-core and SMP read selectively explains parallel aggregation, thread local accumulators, reduction, merge phase. So this thread local accumulators has something with to do with branch folding, with complete buffer queue, ROB. This connects to two-phase aggregation, BigQuery distributed execution, vertical parallel group by. What is not in the inside the machine, very important for your mental block. Topic query planners, book not covered. Topic SQL execution, book not covered. Topic LSM trees not covered. B trees not covered. Those come from designing data intensive applications, database internals papers, BigQuery slash Vertica docs. Inside the machine explain the CPU reality that forces those design. Even the OS, so the CPU, the OS works based on those CPU architecture reality. Just like the three easy pieces, OS 3 easy pieces. How this ties to everything we discussed. Here's the exact mapping, concept, bitmap, and slash or. Inside the machine, chapter 3, ILP, SIMD. Then column scan, chapter 4, cache lines. Predicate pushdown, cache 3, chapter 3 plus 4. Aggregation, chapter 3, tight loops. LSM sequential IO, chapter 4. Why Firestore is slow for analytics, chapter 4, pointer chasing. Why it suddenly clicked late? You read the books in this order. First, OS 3 easy pieces, abstraction. Second, networking protocols. Third, data systems, which is algorithms. Fourth, CPU, physics of execution. Most people read CPU first. You're now closing the loop, which is why it feels disorienting but powerful.